Hey, good afternoon. My name is Prasoon Diwan, and I'm going to talk about a project that involves a diverse set of partners, and I'm going to represent today the computer science aspects of the project. And I'm going to start by explaining what I mean by data science. Okay, so data science is making inferences based on data in various fields, and that's a very high-level functional description of the area. I'm a systems guy, so let's go and look at a little bit of, on how it's done, the implementation. So you take some data, you run it through a program, and you get some output. Often a single program will not produce the ultimate output, so you chain these together. And since we're making inferences, the inferences can be wrong. They can be false positives and negatives. So there's sometimes humans involved in correcting the data. And humans are involved in other roles too. They can collect the initial data, they can write the programs that process the data and modify the programs in response to the corrections made. So there's a need for synchronous and asynchronous collaboration. That's one requirement. You often have to repeat the steps with different examples of data, and these steps have to be merged. So the workflow you're creating is more complex than just a simple linear workflow. You're creating a graph. So you need a mechanism to interactively specify these workflows in a flexible and easy way. And often you have big data, so you need computation cycles also. Okay, so we understand data science a little bit better now with these requirements. And these requirements are independent of the field. So you'd like to meet these requirements in some common infrastructure. That infrastructure is going to provide you with some virtual computers to meet the computation cycles requirement. That's why it's called a cyber infrastructure. You'll have some mechanism to do asynchronously share data. Okay, so that's another requirement that's met. And what I'm going to focus on is workflow composition. I'll consider these two problems as solved and look at workflow composition. Now, if all you're interested in is flexible workflow composition, then actually the problem was solved like 50 years ago in Unix by a tool that you might have used. Shell. Okay. So you can connect programs together using I/O redirection and pipes. You can repeat parameterized steps using loops. That's something that exists in the shell. And you can use loops and regular expressions to merge results together. Okay? The reason why there's only one person who said shell and not the others was because shells are hard to learn, hard to use, and are rarely used as a result. So that's the problem. That we have flexible workflow composition, but we also need something that's easy to use and learn. Okay? And if you want these two requirements to be met, there are two general principles you can employ. One is to replace textual descriptions with visual descriptions, and the other is to do steps automatically for the user. Okay? When you do things automatically, you lose flexibility. So that's a fundamental trade-off, and that's why you have this pyramid structure here. Okay? Now, these principles have been known for a long time, for more than 40 years. Command languages have existed for 50 years. But it's only recently in a system called Cybers, which is an NSF project at University of Arizona, that people have successfully used these two principles to simplify command languages. Okay? And they've come up with two layers. One layer goes and allows you to create simple workflows, no loops, okay, interactively. And the other layer assumes that the workflow has been created for you, and you just have to you're just navigating the workflow and looking at results and editing them. Okay? So let me just give you an idea how these layers might work. So this is discovery. You want to create a pipeline, so you search for the programs using your regular search tools, and here we're looking for something that does trimming for us. Okay, and we get two answers. We go and select one, and we've got the first program in the pipeline. Okay, so we're not typing anything, we're just using a GUI to select. You can similarly add some more programs in the pipeline. You haven't done any connection of programs right so far. And now you're going to connect the output of a program to the input of programs further in the pipeline. Okay? And the system knows what the programs are, so it can give you a menu to do the selection, and you select from menus, and you've got a pipeline. Okay, so that's discovery. This is the DNA subway, which is where you're given a flow already. Okay, and all you do is go from node to node, like you go in a subway, because they use a subway model. So here we are in Blast N. We go to another node. We can go and press the run button. And now we can now the program has been run. We go and press the view button, and we can look at the output, edit it, and so forth. Okay? So these are, so you get to see how one can use visualization and abstraction to make the system easy to use. Okay? And this is, like I said, is a big deal. This system attracts about 500 new users each month. Okay, so that's a test that this technology is usable. The problem, though, is that you get today either flexible workflow composition or you get easy-to-use workflow composition. You can't get both. Okay? So there's this trade-off. And the second problem is that if you want, we already know that command language is difficult to learn and use, and the visual languages are non-standard. They're not well documented and ever evolving. So either way, people are in trouble when they get to use these technologies. So these seem like inherently difficult problems, unsolvable problems, but that's the purpose of this project, to address these problems. Now, when I was growing up and we had tough problems, the most powerful solution that we always thought about that was common to all fields was indirection. In today's world, of course, the answer to almost every problem is machine intelligence. Okay? So let's see how we can employ that here. We want to create a new system, Cyverse, where the idea is that the cyber infrastructure not only supports data inferences, but uses data inferences to make the system easier to use. Okay? So that's the basic idea behind the project. Okay, now how that translates into, gets fleshed out, that's to be decided. But the idea is to create this self-feeding cycle where the symbiotic relationship allows cyber infrastructure to improve inferences, which improve the cyber infrastructure in turn. So what might that really mean? Oh, this formatting got destroyed by David here. I'm going to blame him. So we've got somebody wrote P1 less than F1, and on the same line, try to put a pipe symbol, and doesn't quite know what the next program should be. Okay? So presses the tab button. Normally the tab button, the tab key will give you the files in the current directory, but this tab is more powerful. It says, okay, the programs to complete are P2, P3, and P4 in that order. Okay? And somehow the system figured that out. And this person doesn't know any better, so they choose the first program, and that works. Okay? So what's going on there? The system is keeping track of how various people are connecting programs together, what parameters they're passing, and based on these features, making recommendations of how to complete this particular pipeline. Okay? So this is a recommender system, and you might think that, so this is, we're not talking of large amounts of data. We're talking of data commands that are entered by users, so there's only so much data you can enter. So neural networks are not the candidates here. And what you're doing is graph mining. Okay, I've got a graph here. You're creating recommendations as a recommender system. And the actions of one user influence what other users see. So that's collaborative filtering. And what one can expect is an algorithm in the intersection of these fields. And actually there are a few algorithms that are good candidates. And the project here will involve, and these are waiting to be combined. So the project here will involve combining them and evaluating them, okay, and based on existing data, and then extending them, of course. Okay, so this assumes that we have enough people who've traversed the graph so that we can make recommendations. So the question is how to seed the system and how to address idiosyncratic situations. So here we have Bob, who should enter P1 but enters P. System says, sorry, command not found. Says, okay, let me change the directory, knows about this, and says, sorry, no such file or directory, tries a few more steps, and none of them is really making any progress. Okay? So fortunately, there is a helper, Alice, around. Bob doesn't really go and ask for help, but the system figures out, based on these command patterns, that Bob needs help, and that message is sent to Alice. Now, you can have false positives. So Alice executes a new shell command saying, give me the history of Bob, a remote user. Verifies that this is not a false positive. Well, Bob might or might not want help. So uses another shell command to go and send a message saying, hey, do you need help? And he says yes. And then uses yet another command to join Bob's session so that now Alice's commands are being executed in Bob's context. Okay? So there's collaboration here. And finally, so Alice's commands are now replayed in Bob's context. Okay? So what's going on here? Again, small amount of data used to make inferences. And here we don't expect to come up with a new machine learning algorithm. We expect to use an existing algorithm with new features. A student of mine completed a thesis on automatically detecting difficulties in Java programming, and we hope that we can extend that work or change that work, adapt it to command languages and the graphical user interfaces that CyberInfrastructures provides. Okay. So this assumes that we have synchronous help available, okay, and this is very targeted at training exercises where there's a trainer around, okay? And it provides individual awareness of progress. You don't really get a bird's eye view of what's happening, okay? And so what we need is some kind of dashboard. And the key idea here is that we will use the existing visualization that Cybers has for navigating. So this is a particular visualization that assumes there's a predefined workflow. What we'll do is build this workflow dynamically based on what others are doing, and then we can go and see how many people have reached a particular point in the workflow, and then drill down and see who's got trouble and what exact trouble there is. So there's this awareness engine also. Okay? So let me give you the big picture now. So we assume that there's a training exercise, and today in such exercises the helper has physical awareness of the local workers and provides physical help. With our new system, we can go and provide help to remote workers, get scalable visual awareness of what's happening to them, and provide remote manual help. And what's even more interesting is that the help can be provided automatically by the system. Okay? So that's the big picture. Now, how do you evaluate the system? Typically, those of you who've done machine learning, you have some benchmark data, and you go and measure on that the precision and recall or other metrics. Here, we've actually got real exercises, so you can actually see what impact you're making. And based on the project we wrote to NSF, there's a bunch of courses and conferences that have expressed interest in using a system for that. And so that's good, because you'll also learn something about the domains that you're supporting through this research. Okay? So here's the system at an architectural level. So you've got difficulty detection, you've got difficulty resolution, the recommendation, you've got this progress awareness, and they're done in a server that can be accessed by clients that use the command line, or clients that support the visual interface, and maybe some standalone clients too. Okay? And some of you may have written the shell. And typically that's done written in C, and it provides a subset of the commands that a regular shell provides. What we will do is use the shell to write the new shell. Okay, so we'll use a bootstrapping approach, and I looked this summer, and I think the shell is powerful enough to do that. Okay. Similarly, we don't want to go and rewrite the Cyber's visual interfaces, so we'll just use Chrome plugins to go and extend the existing interface. So that's an implementation level thing. And the project can be decomposed into the following components: the help recommendation, difficulty detection, shell extensions, and so forth. And for each component here, I have outlined what particular aspect that you will learn in particular with that project. And also, since this is part of a bigger system, you will also get some broad expertise in all of these issues. Okay, because this is an interdisciplinary project. Now, I haven't, so I've got one or maybe two RA positions and a bunch of 991 projects here. And I haven't distinguished between them, because each component can get a publishable result in a semester of work or so, I believe. And this project, NSF project, just got funded, so we've got 3 years. It can be one person doing the work over 3 years, or a bunch of people doing work quicker. And so that's a project, and come talk to me if you're interested in either working on it or if you just have ideas. Okay? And I'm actually 12 seconds ahead. Thank you.